Alright, so in the previous calculus video, this is where we stopped. In fact, I wrongly and foolishly concluded that there is something wrong with this exercise. There is nothing wrong actually. So let's solve this. Let's find the value. We have this limit x squared plus 8 its square root minus 3 over x plus 1. So we do the usual trick, that is this. We multiply and divide by this quantity, which you can see is non-zero because this is non-negative square root, and in fact since x appears with a square, it's not just simply x, it's x square. So x square plus 8 is at least 8. Even when x is negative, this cannot be less than, you cannot reduce it beyond 8. So anyway, this is positive, this is the positive real number. So there is no harm in multiplying and dividing by it because it will never be 0. Now in the numerator we of course can use our a square minus b square formula, and that will give us this, and the denominator stays as such. Okay, so now the numerator becomes x square plus 8 minus 9, and the denominator is again that same thing. So this becomes x squared minus 1. And now we can cancel, but before cancelling the common factor out, let's also write one more step where we factorize the numerator as x plus 1 times x minus 1. Now we can cancel this common factor x plus 1 because x is only approaching minus 1, x is not equal to minus 1, and so x plus 1 is in fact, although it's close to 0, but it's not actually 0. And which is why it makes, this expression makes sense because of that thing. Had x been equal to minus 1, this would be meaningless. So after the cancellation, we have this. And now there is no problem in applying theorem 1, that is the several parts of theorem 1. For example, first you apply the quotient rule. That will allow you to write this limit as limit of x minus 1 divided by limit of this. and then so on. The other rules are then subsequently applied, and finally we get this. Plus 8 plus 3, and that becomes minus 2. So this will be square root of 9, positive square root of 9. So we will get 3 here. 3 plus 3 gives us 6. So that means our final answer is minus 1 over 3. Okay, let's now see the next one. 31. Suppose this one is actually quite easy, but because it's a little different from these things, so let's see what it is. Limit of f of x is 1 as x approaches 0, and limit of g of x is minus 5 as x approaches 0. Name the rules in theorem 1 that are used to accomplish some steps in a calculation, which we will now write. Steps A, B and C. Of this following calculation, and the steps are these. Well, I won't have space for writing it the way the author has written it here. Instead, let me just start like this. Limit x tends to 0 of 2 times f of x minus g of x over this thing. Okay, and the first step is this. And this has been named step A. So in fact there is no need to write a separate solution for this. I mean, we can see precisely what we have done or what the authors have done in this step. In this step, that is in step A, we are using the quotient rule, that part from theorem 1. So it is that. Okay. The next, in the next step, the numerator is this. Which is what you would normally do if you are to calculate this limit. And then the denominator is this. And this has been named step B. So in step B, we have used, what are the parts of theorem 1 we have used? We have used the difference rule, that is the limit of the difference of two functions is the difference of their limits, that rule that we have done in the numerator, and in the denominator we have used the power rule. Okay, that is also one part of theorem 1. So these are the things we have used in step B, but there are others also. So let's see. Naturally, these are the things that come next. Then in the next step, the calculation is taken further, and we have 2 times limit of f of x minus limit of g of x, and in the denominator we have this plus okay, yeah, limit of 7 has been written. And this has been named step C. So in step C, we have taken this 2 outside, which we are able to do because of the constant multiple rule. Okay, because of that rule, that part of theorem 1, we are able to bring the 2 outside. And in the denominator, we have just used the sum rule. The limit of a sum of 2 functions is equal to the sum of their limits. And then of course the authors have not stopped here, but because we are actually given the values, I think I have lost it here. The values were 1, limit of f of x was 1. Have I written 1 here or not? I am not sure. The limit of f of x is given to be 1. Okay, if I wrongly wrote some other value, please correct that. The limit of f of x is 1 and that of g of x is minus 5. Yeah, minus 5 I have written, I remembered that. So this becomes 2 times 1 minus 5, and this is 1 plus 7. We know that if we have a constant function, then its limit is that constant value itself, regardless of where the independent variable is going. So this becomes what? In the numerator we have 2 plus 5, that is 7, and in the denominator this is 8. Cube root of 8 is 2 and square of that 2 is 4. Okay, so you can see what we have done, and in each of these numbered steps or labeled steps, what are the things from, what are the parts from theorem 1 that we have used. So that's it, that's the thing. So I am not again writing something for this. And now the next one is also similar. So I am going to leave that to you. 32 is similar. There also we have one such calculation where steps have been labeled and we have to say which parts from theorem 1 are used in each step, each labeled step. Okay, let's now see exercise 33. Suppose limit of f of x as x approaches c, some real number c, is given to be 5, and limit of another function g of x as x approaches c is given to be -2. Find A. There are 4 parts. Limit of the product of f and g as x approaches c. Part B. Limit of 2 times the product as x approaches c. Part C. Limit of f of x plus 3 times g of x as x approaches c. And part D is limit of f of x divided by f of x minus g of x. So you can immediately see that we have to again use the several parts of theorem 1 here in order to calculate these limits. And without explicitly saying which parts we are using in each of these parts, in each of these limits, we just carry out the calculations. So in A, we can, however, go systematically like this. Instead of straight away writing the final answer, we can show the steps. That way it will be clear which parts of theorem 1 we are using. So by the product rule, this is limit of f of x times the limit of g of x, and they are what? 5 and -2 respectively. So that means this is -10. B. By the constant multiple rule, you can take that 2 outside and now there is no need to redo this again because we already have this value. So this is 2 times -10, which is -20. Then part C, plus 3 times g of x is, if you use the sum rule and the constant multiple rule simultaneously, then this limit can be written as plus 3 times limit of g of x so limit of f of x is 5 plus 3 times that of g of x is minus 2. That means 5 minus 6, which is minus 1. And finally this one. Applying you should understand that when I am saying applying some parts of theorem 1 simultaneously, I actually mean that you should go systematically, stepwise. You cannot apply the constant multiple rule immediately here itself, but instead by simultaneously I mean I am skipping steps. I am not writing all the steps. There is an intermediate step where you should write limit of f of x plus limit of 3 times g of x. That I have not written, but instead I have directly written this. So that's what I mean when I am saying that simultaneously using this and that. So here in that sense, simultaneously using the quotient rule and the difference rule, this limit equals and now you just have to put the values. But let me remind you of that little caveat that you have when you are applying the quotient rule, namely that ultimately you should not end up with a 0 denominator. If that happens, then the quotient rule is not applicable. In this case, however, it won't happen because now we will see what is limit of f of x. 5. And that of g of x is minus 2. So we are not getting 0 denominator, we are getting the denominator 7. So that is okay. So that's how we have this. And the next few exercises are similar. So I am leaving them. 34, 35 and 36 are similar. Okay, so you go through them, you try them out and see if you can get them. You obviously will be able to solve them. It's almost nothing. It's just an exercise that is there for you to try. That's it. And let's now go to limits of average rates of change. This is something that is going to be important later on when we encounter the notion of derivatives, differentiation. Limits of average rates of change, and I need a little ink, I think. The light is flickering. I think it's going to go out anytime soon. Okay. So there are some things here. Let me just first write those things, because because of their connection with secant lines. Secant lines, tangents, and average rates of and instantaneous rates. Okay, limits of the form. Limits of this form are very important, and they occur in calculus frequently. And in fact, this is how we will eventually define derivative of a function. Occur frequently in calculus, yes. And which is why it would be nice that we now calculate some such limits. Okay, limits of average rates of change. You can see that we have in fact encountered this type of thing already. This is the average rate of change of the function f in this interval. Assuming that h is positive. If h is negative, this x minus h will be the left boundary point, x will be the right boundary point. That is understood. Okay. So average rate means you consider the f value at the final point and the initial point, and you consider their difference. So that is the change in the value of f in that interval. But then you divide by the length of the interval, that gives you the rate at which the function changes in that interval, that is the average rate. But then as you let h approach 0, then the interval shrinks, it keeps shrinking. So you get instantaneous rate of change of this function f at the point x, because as your h is approaching 0, this x plus h is going, it gets nearer and nearer to x. So considering this is almost like calculating the rate of change of the function at the point x itself. Okay, so that's why instantaneous rate. And this thing is related to not just instantaneous rate, but if you interpret these things geometrically, if you draw the graph of this function and then look at all these things, you get tangents, secant lines. We have already discussed these things. Okay, so now it has started raining heavily. In exercises 37 through 42, evaluate this limit for the given value of x. And function f. And here also we are not going to solve all of this, but I will just solve 2, leaving the rest to you. They are all similar to one another. So let me just pick the 40th one. Here the function is the reciprocal function and the point is -2. Okay, so for these things we have to calculate this limit. So let's do it. This will be, okay, what is our x? Our x is -2 and the function is the reciprocal function. So -2 plus h are the same thing, h minus 2 1 over -2 divided by h. Okay, so this becomes what? 1 over h minus 2 plus 1 over 2 divided by h. Now if you take LCM and do your usual calculation, then you get 2h times h minus 2, and in the numerator you get 2 plus h minus 2. And now you can cancel h because h is actually not equal to 0 but just very close to 0. And now you use your rules, that is quotient rule, then product rule, then difference rule. After doing all those things, you ultimately get this value. So that means our final value is minus 1 over 4, that is minus 0.25. So this minus 1 over 4 is the rate at which the functional values are changing at the point -2. So it's that instantaneous rate. And it is also, if one draws the graph of this function and looks at the point on the graph where the x coordinate is -2, the y coordinate of course will be -1 over 2. So at that point, if one concentrates and one draws a tangent to the graph at that point, then this -1 over 4 will be the slope of that tangent. Okay, we already know these things. So let's pick another one, 42. Here the function is square root of 3x plus 1 and the point is x equal to 0. In writing this limit, there is it's tempting to take x approaching 0. I don't know why, but sometimes I feel like writing x here, maybe because we are used to taking x there, so that will be a terrible mistake. So whenever you are trying to write this, you please make sure that the variable of this limit is actually h, and although here x looks like a variable, but x is a fixed value. For that h, x is fixed. Okay. And our x now here is 0. So actually we are, let's just write that so that we will make less mistakes. Okay, so now we use the definition of the function 3h plus 1 minus what will be f of 0? 1 over h. So it's again in a form just like exercise 30. So we have to also proceed accordingly like that exercise. What we did there, here also we have to do a similar trick. That means we will have to multiply and divide by this. And again I am saying that this is possible because this is non-zero. How that is non-zero we have already seen in exercise 30. So I am not going to elaborate on that anymore. But now the numerator becomes this. And this is the denominator. And one more thing that I forgot to say something about in the in exercise 30 is that when we lift this square root and write 3h plus 1, we are assuming that 3h plus 1 is a non-negative real number. Okay, so that thing is there. There also we did this, and here also we are doing it. So if I skip one step and cancel 1 and minus 1 h and h, then I am left with this. And then applying the several parts of theorem 1, we ultimately have this. So that means the instantaneous rate of change is 3 over 2 of that function at the point x equal to 0. Okay, so that's it. That's the solution. Now before I finish this video, let me just see one more thing. You see, I said that while lifting this square and lifting the square root means while making it vanish, I am assuming that 3h plus 1 is what? Is non-negative. Is that true? Not necessarily, I think, because h is approaching 0. But if h is negative, then what will happen? If h is negative, is it guaranteed that this will be non-negative? You think about this part, okay? If there is a potential for 3h plus 1 to be negative, then square root of this will not be equal to this, which is why we do not write this. I mean, we write it of course, but that is a calculation in the realm of complex numbers. But right now we are dealing with real numbers, real functions and all those things. We have nothing to do with complex numbers or non-real complex numbers. So this part, you think about this part, okay? I will also think about it, and then let's see if there is any problem. A hint is that you have to see what the domain of this function is. Since we have square root, so of course the domain cannot be the entire set of real numbers. For example, in particular, say x equal to -1, you cannot take, because if you put -1 here, then inside the radical sign you are getting -2. That is not a real number. Since we are assuming f to be a real valued function, so -1 is not an element in the domain of f. So you go back to how we found natural domains, and from there you will get an idea of how 3h plus 1 is non-negative. I believe it will be non-negative, but there should be a reason, right? So you please do that, and that's just it for tonight. Our next upload is this coming Friday, and on Friday let's go back to vector spaces. So that's just it. So see you on Friday with vector spaces. Until then, this is me, Lucifer, from A Mathematical Group. Have a nice night.